Whenever a regression analysis is run, SPSS gives us something called the adjusted R-squared. This is also referred to as shrunken R-squared in the literature, so just so you know that those two terms refer to the same thing. When we have the situation where the number of our predictors is starting to approach the number of cases in our data set, we have a situation where R-squared becomes artificially inflated. And it is not significant. So it is this weird situation where we have this large R-squared, but it's not significant, and when that happens, we know that the R-squared is kind of lying to us. And so we have adjusted R-squared, which applies a correction that gives us the true R-squared. So this often happens when we have when we're doing applied research and a client asks us to run some analyses on a data set with maybe 60 cases, but there are 45 predictors, and they want us to tell them which of the predictors contributes the most variance in the DV, and so which one is most important. And so you would run them all in, those 45 predictors, and then you would have this situation where we have an artificially inflated R-squared. So we have the adjusted R-squared that shrinks the R-squared back to its proper value so that we can trust what it's saying. So here's the formula for doing that, and there are a couple formulas in the literature at least, but this is the one that is widely used, and I believe it's the one SPSS uses for its correction. I want you to notice the various elements of this formula and understand what happens when we hold all else constant and we increase the n size, and then we hold all else constant and we increase the k, and what happens to the entire formula. So the R-squared in that formula is our observed R-squared, so set that to a value that's easy to calculate, like 0.4 or 0.6. It's totally up to you. 0.6 is kind of large, but it doesn't matter. This is just for learning. So set that to a value, and then when you have that set, plug in a certain k, so k equals 4, for example, and then adjust the n to two different values. So make the n 20 at first, calculate the formula, and then make the n 100, and just see what happens. So take a few minutes at this point, get out a piece of scratch paper, and do some experimenting with this. And what you'll see is that when we increase n, everything else constant in the formula, the observed R-squared and the adjusted R-squared will converge. And that means our observed R-squared is more trustworthy. We don't have to apply a big correction because as n increases, we don't have this issue of our k approaching n. However, as n decreases, the observed R-squared and the adjusted R-squared will diverge. So the observed R-squared is less trustworthy in that case, and we would want to use the adjusted. So notice how that works. So at this point, switch and hold the n constant and increase the k. So set the n size to a certain value like 100. Keep the observed R-squared at the same value that you had it, and then do this formula with a k at 4 and then with a k at 80, and watch what happens. And what you'll see is that as k increases, our observed R-squared and our adjusted R-squared will get further away from each other. And conversely, as k decreases, they will converge. And in that case, the observed R-squared is more trustworthy, and it doesn't need a large correction. Remember the idea that when we increase k, we're also lessening the chance that our F statistic will be significant. So all these factors are playing the same role that we've seen before. It's just a similar pattern kind of what's going on, and that is that when we have too many k, we're going to lessen the chance of finding a significant F test, and we will artificially inflate our R-squared. So it'll be, again, a large R-squared, but it will not be significant, which is odd. Typically, it's not that way, right? The larger the R squared is, the more chance it has to be significant. But with too many K, this can happen, this odd finding. So please know this, understand what's going on here, and if, let's say, I gave you a homework problem or an in-class work problem where there is 100 cases in your data set, but you have 90 predictors, then you find this very large R squared, what's going on? And you could explain this idea. Now, if your client does give you this assignment and you have very few cases in your data set compared to the number of predictors, then is there anything that you can do? Well, if there are a lot of predictors in that data that the client wants you to run, chances are that they are probably redundant with one another. So they probably, at least a few of them, probably correlate highly with each other. And remember, when we have that high redundancy, that multicollinearity, that's not good for our model anyway. So again, we want to be parsimonious with our predictors. So one possible solution that I've put in the bottom of the slide here in the notes is that you can do an exploratory factor analysis, which you'll learn next quarter, and you can and there's a YouTube little video to show you how to do that in case you're interested. And once you've identified how the variables coalesce into certain factors, so what an exploratory factor analysis does is it takes all of those predictors and it shows you the ones that are correlated highly with one another. And so let's say your 20 predictors are reduced to 4 because certain ones correlate very, very highly with each other, and so then you would have 4 factors. And so basically what you're doing is you're grouping your predictors and averaging them into 1, and so you're taking, like, let's say 5 predictors correlate highly with each other. So you take them and average them together and treat them as one predictor. And so when you do that, you're basically doing a data reduction method, which is great, and you can reduce the number of predictors in your model without, hopefully without making the client concerned in any way. So you're doing a truthful analysis that hopefully will please the people that you need to, who you're doing your work for. So, and it's also a truthful way. It's not altering the data in a way that would be inappropriate in any sense. So this is a data reduction technique. You'll learn more about that next quarter. But what you can do again is you can take 20 predictors and you can correlate them all with one another and see how they coalesce and group into factors. And then take those factors. Hopefully you're going to reduce your 20 predictors into maybe 3 or 4 primary factors, and then use those factors as your predictors. And that will provide a much better picture without having an inflated R squared like this. Again, you can also just look at the adjusted R squared, but a lot of times that's not helpful, but it's still a truthful way of looking at your data.